Can I do an introduction? I would really like. So, please welcome Maarten Frens. Maarten Frens is full professor of systems neurophysiology in the neuroscience department, and he's been teaching this course in linear systems for our neuroscientists for a little while. Yes. And he's also the vice dean for education in our university. So, if you have improvement suggestions for the computing brain, give it to him. And yeah, so I think he is going to be expressing that fundamental idea that we can simplify parts of the brain, and we should simplify our understanding in sort of a constructive way, and try to synthesize. Brains are neurons, but not they're not nanoscopic entities. So, without further ado,
I completely have to change my lecture. Yeah, guys, welcome. Or, I mean, you were already here and I just arrived, but very nice to see you. You know that the most frightening thing to the brain or to humans, it's basically the same, is unpredictability, right? That's what is fearsome. And in that sense, teaching to minor groups is the most frightening teaching that you can do. This. Because I know so little of your backgrounds. Some of you may know much more about the stuff than I actually do, and others may have a hard time grasping even the most fundamental concepts. So what I'm hoping that's going to happen in the next, I don't know, 1.5 to 2 hours, is that at least we can have like a fruitful interaction and a debate. And I'm sure that I will offend the knowledge and the intelligence of some of you, hopefully mostly in the beginning, with stuff that you already knew. I'm sure that at some stage I'll be using words and jargon that you've never heard before, and then please interrupt, because there's probably other people in the room who have a hard time in grasping what I'm saying at that moment as well. So let's try to work on this together. My synopsis of what I was planning to tell is a little bit different from what Mario just said. So what I want to do is show you, well, first do a really quick introduction on linear systems in general, and then show you how, as an experimental scientist, even having a very, very simple grasp of that sort of theoretical thinking, can help you tremendously in understanding the experiments that you do, being able to set up the experiments that you do, being able to predict what it will probably look like once you crack open the brain and you're actually looking in the brain, and then verifying whether this is true, and therefore get into a mode of hypothesis testing rather than just moving into the most complex organ that we know of, that's around anywhere, and just start collecting data and hoping that at some stage they will make sense. All of the experiments that I will describe are quite straightforward, and they were all done in the late 60s, early 70s. Not because nothing has happened afterwards, but that's basically, and we saw that from Mario's lectures, well, that's the time when the really good stuff actually happened. And I won't claim that it has been downhill ever since, but it's just adding levels of complexity, right? Whereas the fundamental insights happened at that time, and I think that you guys are at this stage in your education better off in understanding the underlying principles well, rather than knowing the cutting edge level of where we are scientifically, these things. Okay, so let's see what happens. I've done this last year for the same minor, but obviously different students. That worked out relatively well, but ended a little chaotic. So I don't mind chaos, and let's see what happens. So first of all, let's figure out and make sure that everyone knows what it is when we are referring to a linear system, because title of my talk is Linear Systems in Neuroscience Research. And once we've established that we all know what a linear system is, what use is it for us once we start designing experiments, doing experiments, etc., etc. So how can we deal with a linear system? How does it help us to know that a certain system is linear, or at least we can consider the system to be linear? And all of this, so I'm a biologist by training, right? But all of this starts from engineering. And so if you're an engineer, then obviously your goal is to make things, complicated things, simple things, but things that work. Us, as we are here, well, maybe some of you are engineers, that's part of the unpredictability, but the point of doing neuroscience research is not so much to build a brain or to design a brain, but to have another completely complicated system that's already there. And then understanding the underlying design principles. So we're not designing a leopard, but we'd like to know how the leopard is designed. And so linear systems theory stems from people who build stuff, and what engineers do is engineering. And so what we're going to do is we're going to do reverse engineering. We're going to use the same type of principles, the same type of theory, not so much to be able to build stuff, but to understand how existing stuff is built. And how do you do that if you're a physiologist? Basically, what you do is there's some big problem. Let's say the question is, and I think many of us, maybe including Mario and myself, came into the field of neuroscience saying, I'm fascinated about how the brain works. Brain and how it works. Yes. So that's a big problem, right? So actually two big problems. But so you start by looking at a big problem, and then you're chopping this big problem into smaller pieces. And actually you make the pieces so small that at some stage they are so small that you can solve them. And you write a paper. You've solved a small, tiny little fraction of our knowledge on how the brain works. And then the idea is that if you've solved enough of these separate tiny little problems, that you can glue all the answers together. And if you have the answers to all the little problems and you glue them together in a proper way, then you find the answer to the original big problem. That sounds a little naive, because it is a little bit naive, right? This, and we're far away from the really big problems. But as long as we make some assumptions, and that's where the linearity in linear systems comes in, as soon as we're making few assumptions, all of this actually becomes a lot more feasible. And this means that basically what we're doing, if we're doing the systems approach, we take a black box, a system. We try to open this black box by experimentation. We're looking inside the black box. We're doing recordings from the black box. We're recording behavior. We put people in MRI machines. We stick electrodes on the skull or in the brain. Then it turns out that in this black box, there's a huge number of smaller black boxes. And then everything starts over again. And we try to solve all of these smaller black boxes and then try to fit them together. Okay. Before we move on to what's special about linear systems, let's first ask ourselves, what is a system? A system is basically anything that has an input, so there are signals going into our system, and then it reacts with an output. So a system is a transformation from transformation and information. There's stuff going in, there's the system, and it results in some sort of output. That's the system in the broadest sense. And because it's so broad, this also means that it almost becomes silly if you think about examples of systems, because you could say that, so what's not a system, right? Basically everything is a system in the sense that there's inputs to it and it's responding to it. And it also means, because this also looks a little bit like a formula, right? So a formula has an input and has an output. Then actually our goal is to try to describe systems as formulas, because once they're formulas, you can work with them. Graphically, we have a system over here. So suppose we have some input, and this input could be something that varies over time, right? And then we're recording the output, and then the output is something that varies over time as well. If we know the output and we know the input, then by a lot of knowledge that has been accumulated over the centuries, we sort of know what type of process is going on within our system. So typically this system would be something, if we compare the output and the input, if we keep this very qualitative, then this system is something that seems to cut off the sharp edges, right? And it's sort of smoothing whatever is getting in there. So the system is making signals smooth operating. Again, we have time varying input here and we have time varying output over there. Your input and your output do not necessarily have to vary over time. They could vary over time, over space. If you're a filter on a photo, for instance, then it's over space. A varying input and varying output. Yeah, I'm sure I wanted to say something else about this. Escape, and I'm sure it'll come back once we're 3 slides down the road. Oh yeah, I know what I wanted to say. That is, obviously, this also means that if you're doing experiments, right? Maybe we're jumping a little bit, and you want to know what's in your system, it's always important that you bring yourself in a situation that you can very accurately record whatever the output of the system is. The output you do not know in advance. And for the input, there's basically 2 options. Either you put yourself in a position where you're completely in control of your input, so you're providing the currents, you're providing the stimuli, etc., etc. Or you can record the inputs at least as good as you can record the outputs. So let's assume that this is a brain cell, a neuron in the brain somewhere, and this brain cell is receiving input in a healthy brain, and it's generating action potential, so it's generating output. If this is a healthy system, then very often we may not be able to completely manipulate whatever is coming into the neuron, but we can record what's getting in there, we can record what's getting out there, and then we can still see the process that's going on. Any questions? Good. Okay, so what sets linear systems apart from non-linear systems? That is, something that's called, that's the main one, the superposition principle. And what does the superposition principle say? That is, and let's look at this, and then we'll look at the quick and dirty test. If we have a system, and we know that if we provide input X, which can vary over time, right? And this results in an output Y. Remember the last slide that I showed you, the input to the output. And we provide some other input, and that's resulting to another output. Then a system is linear if once we feed the sum of the 2 inputs, 2 separate inputs, then the output of the system is also the sum of these 2 separate outputs that you see over here. So if we feed X, we get Y. If we feed Z, we get R. If we feed the sum of X and Z, then we get as an output Y and R as a sum. The quick and dirty test for linear systems is basically a special case over there, right? If you say, if I have an input and this results in an output, then if I double the input, this is what everyone does in the back of their heads if they're thinking about linear systems. If I double the input, then the output should be twice as big as well. That's basically a special case over here, because then this is x plus x equals y plus y. Right? So what could be if you have a system and you know that's linear, what's the huge advantage for me as a person who's trying to figure out the brain or what's going on if I know that I'm dealing with a linear system? Yes? Yes. It's predictable, or at least in the sense that I can extrapolate, right? I can now, once I've recorded a limited number of conditions, I can